Hello, in this video I'm going to make a start on magnetic fields, and this will sort of build up to then in the next video we can go through meaty topics like electromagnetic induction and transformers and things like that. But let's start with the basics here. So magnetic fields, then, where do they come from? Well, they're created by moving electric charge. So it's not like with electric fields when we were looking at those, if we've got a particle that's got electric charge, then even if it's just sitting there and you've got static electric charge, then you've got an electric field around this static electric charge. Magnetic fields, you need to have moving electric charge. You need to have a changing electric field that then creates that magnetic field. So this adds a sort of layer of complexity over magnetic fields, particularly when we're getting started, that we don't see in the electric fields. But if you've got moving electric charge, which we get in all manner of different places, that then creates a magnetic dipole. So what we mean by a dipole is it's got two poles. So we get the north-south of a magnet. You don't get monopoles as far as we know. You don't just get a north or a south on their own. They always come in pairs. You get magnetic dipoles whenever you've got moving electric charge. And as I say, we get moving electric charge all over the place. Obviously, you've got a current carrying wire. That's got moving electric charge. Orbiting electrons. So each atom, you've got moving electrons. You've got the nucleus and you've got electrons doing their thing around the nucleus. So you can think of each atom as being a mini magnet. It's going to have a mini dipole. This is the basis of magnets that we use. That if you can align all of those atoms, they might be all over the place, not aligned. You might have north south, in different directions. But if you can, and these directions might be changing, but if you can align them so they're all north south, north south, north south, then you've got yourself a magnet. This can happen in a number of ways. You might get a permanent magnet. When you're rubbing a magnet on some iron, you can then turn that iron into a permanent magnet because you're aligning all of these dipoles. Or you can have electromagnets where things line up when you've got an electric current flowing. So there's lots of different ways that these things can be set up. I mean, you get naturally occurring magnets as well, lodestones. This is magnetite, which has been it's all been aligned, so it is just a naturally occurring permanent magnet. I think the leading theory on that is when you get lightning strikes on certain materials and then it causes this permanent magnet effect. So we've got that as well with an orbiting electrons. Of course, electromagnetic waves, we've got changing electric fields in those, and this is how the electromagnetic waves are propagating. You've got the changing electric field that creates the changing magnetic field, which creates the changing electric field, and so on and so forth as it's propagating through space. So we've got a lot of places where we've got moving electric charge, and that's where we're then getting these magnetic fields. Now, this means, as I said a moment ago, we've got this extra sort of level of complexity because we always really need two fields in this. We need to have two things happening in order to see anything that's going on. We need to have some kind of current in order to have our moving electric charge. And then we need to have some other magnetic field, which is then interacting with this moving charge. So it's like having two magnetic fields which are then interacting with each other. So we've got this sort of multiplication of stuff we need to look at when we're analysing magnetic fields. So let's get some examples of that to make it a bit clearer what I mean. So let's go to the current carrying wire then. So say you've got this wire, so this is going in and out of the screen. Let's say the conventional current is coming out of the screen at us. So, the dot, the usual convention of the dot in the wire for coming towards you. And, if it was going into the screen, you'd have to cross on the wire. So let's say this is coming out of the screen, our conventional current. Then this current carrying wire will generate a magnetic field around the wire while the current is flowing. And this is a circular magnetic field. And the direction of the magnetic field, and our magnetic fields we draw our arrows going north south when we've got our dipoles, And when they're going round wires like this, we've got, I mean, obviously there's maths behind it, but we've got the easy way of saying using the right hand grip rule. So we point our thumb in the direction of the current, so that'll be going straight towards us out of the screen, and then our fingers on our right hand will give the direction of the magnetic field, so we'll be drawing them anti-clockwise in this particular case. So here's one case then where we've got moving electric charge generating a magnetic field. So now, though, I mean, this isn't doing that much on its own. At least we've got a magnetic field. But we're then mostly looking at, well, let's put that inside another magnetic field. So say we had a north-south going on here. We've set up this external magnetic field to the wire. This is going to have field lines that, well, in the absence of the current carrying wire, they'll just be going straight across with this uniform magnetic field with the arrows going from north to south. So great. What happens when we got a current carrying wire in there? We're now going to get an interaction between all of these things, between these magnetic fields, between the current carrying wire and the external field. That's going to interact. And the way I mean, there's a lot of ways of thinking about this. I mean, there's the maths behind it, which we're not going to get into. I mean, because when we're doing pre-university physics, we don't get onto vector product, the cross product, and all of the maths behind this is going to be using the vector product, which we don't know how to do yet. I mean, some of you might be doing further maths, in which case you will come across this. But yeah, we're going to be doing various cross products, which we're going to have to leave out at the moment. But visualizing this pictorially, you can imagine these magnetic field lines here being sort of brushed under as these field lines are turning anti-clockwise. It's like they're pushing the field lines underneath. So you get this effect where these magnetic field lines are going underneath the wire, and there's like you can imagine a catapult effect of the wire being pushed up in the air. Now, of course, this is an analogy in order to try and maybe remember what might happen. This isn't an actual description of how the world works. This is all going to be described in quite complicated mathematics and theories about fields and how they interact. But at least in terms of visualizing things, that's one way of getting going. We have another way of talking about, or at least predicting and saying which direction the force is going to be acting, because we've got Fleming's left-hand rule. So that's the one that seems to get pushed on people. So we've now swapped from right-hand grip rule to left-hand Fleming's rule. And this is where we're assuming that everything is perpendicular to each other. We've got these three vectors in perpendicular directions. So you're going to have the magnetic field, the current, and the resultant force. So if you're saying that we've got the magnetic field saying going that way and the current going that way, with Fleming's left-hand rule, we're using our thumb and first two fingers to replicate these axes. And we're going to say, okay, right, we've got our first finger, we point in the direction of B. Our middle finger, we point towards us, coming out of the screen in the direction of I, in the direction of our conventional current. And then whatever direction our thumb is in, that will be the resultant force, which in this case will be upwards. So this is our Fleming's left-hand rule that gets pushed on people. So this is just a way of knowing how to say what direction the force is going to be if you don't know how to do all of the maths and everything else, if you don't know how to do vector products yet. That's our Fleming's left-hand rule. I don't actually use Fleming's left-hand rule, but sometimes they ask exam questions where you have to actually say you use Fleming's left-hand rule. It's really annoying. I use what I refer to as the right-hand slap rule on this. So you have, in this case, you use the right hand. You'll put your fingers, so you just have a flat hand rather than having to do this stupid thing where your fingers looking like three axes. You have a flat hand where you point your fingers in the direction of the field. So it's like you've got if you've got 4 fingers, you're going to have 4 field lines. And then you put your thumb in the direction of the current. So you'll have your right hand with your fingers pointing off to the right, your thumb pointing out of the screen, and then it's slap for force. It's palm upwards for force. So I go for the right hand slap rule because I just find it easier. Plus everything's then with a right hand rule. Yeah, when it comes to doing exam questions in the UK, at least, you have to say, oh yeah, I use Fleming's left hand rule, even if you don't. But anyway, that's enough of those different rules for figuring these things out. Trying to flesh this out a little bit more then, let's look at this magnetic field, which I've labelled here with a B. This is the notation that we use for magnetic fields when we start out. We call them B fields. This is a vector field. You know, current is a vector because it's got direction. Force is a vector because it's got a direction again, and our magnetic field is as well. You know, we're putting arrows on all of these going from north to south, so we've got another vector field going on here. This is what's referred to as our magnetic flux density, which is analogous to our, you could say that's magnetic field strength. It's pretty similar to electric field strength, gravitational field strength. It's telling us about the strength of the magnetic field, but it's called magnetic flux density, which is partly a historical thing. It's measured in Tesla. Well, that should really be lowercase, I suppose, because the units are in lowercase. Obviously, Nikola Tesla, his name is in uppercase, but the Tesla is the unit of magnetic flux density. And here we can see, if you see what a Tesla is, so this is one Tesla is 1 Newton per meter per amp if we go into other units. So you can see we don't get anything to do with magnetic field strength unless we've got movement of charge in there. So this is bringing us into, well, let's quantify this force depending on that current and this magnetic field strength. And remember, this magnetic field strength is the external magnetic field. It's the one going between the north and the south here. It's not the one going around the wire. So there's an experimental finding that if you set all of this up, you get that the force F is equal to the magnetic field strength, the external one, multiplied by the current in the wire, multiplied by the length of wire that you've got inside the external magnetic field, multiplied by the sine of the angle between the current and the external magnetic field. Now, when we're doing Fleming's left-hand rule or the right-hand slap rule, we're just assuming these things are perpendicular to each other, which to a large extent is taking out the issue of the cross product. Because when you do your cross product, your vector product, I mean, which are the same thing, this is where your sine theta is coming in. It's a way of combining, of multiplying 2 vectors together, in this case B and I. You're multiplying B and I together and the angle between them in order to get a resultant vector. You know, it's got similarities to the scalar product. You might have seen things like, you know, an A dot B being the magnitude of A times the magnitude of B multiplied by the cosine of the angle between them. This is the sort of thing we come across when we do our work done is equal to the scalar product of the force and the displacement. So we're getting 2 vectors here, force and displacement, multiplied in some way, but giving a scalar answer because it's energy, which obviously doesn't have a direction, and energy is a scalar. So we've got one way of multiplying vectors to get a scalar answer. The cross product, our vector product, is giving us a way of multiplying vectors to get a vector answer, which is our F here. But for our concerns at the moment, we've got this empirical finding, and we're going to be dealing with this pretty much all of the time by saying, well, everything's at 90 degrees, so let's turn sine theta into 1. And we're just going to be dealing with F equals BIL. But we can see here this force depends upon having a current, and it depends on having an external magnetic field. And this external magnetic field, if we rearrange that, take out the angle and just say, okay, B then is equal to F over I times L. This is where we're getting our unit analysis here, that our Tesla, the unit of the magnetic flux density, is our force per meter per amp. So you can see we've got that relationship there between force and magnetic flux density and current. So all of that is built in, together. You have to have that moving charge, otherwise we don't have the magnetic field. Right, so anyway, moving on from this then. So if you've got all these electrons moving along the current carrying wire, they're going to be experiencing a force. They've got the interaction between the moving charge and the external magnetic field. If they're perpendicular to each other, we know that force is equal to B times L, I times L. And we know that L is equal to the velocity, the drift velocity of the electrons multiplied by some amount of time t. We also know that current is Q over T. It's our rate of flow of charge. So we've now got that being Q over T, and the T's are going to cancel, which leaves us that the force on the charge carriers, the charges that are moving along the wire, is BQV, with V being the drift velocity. Obviously for an electron that would be BeV, because the charge on an electron, the Q, is equal to V. So we've got not only a statement of what the force is on a charged particle moving in a magnetic field, which is what this is. So this is the force on a charged particle moving in a magnetic field. But that force is perpendicular to the motion of that charged particle. So we're moving into the realms of circular motion here. We can say that is our centripetal force. That is going to be equal to mv squared over r. Cancel the v's, and we've now got ourselves circular motion, and we can say what the radius of that motion is going to be. So r is going to be equal to mv over bq. So we're now getting a crossover here between electromagnetism with our magnetic fields and our current carrying wire, and classical mechanics and the work that we've done in that. So you can see here that our radius is going to increase as m and v are going up. So if you've got a heavier particle, it's going to move in a wider circle. It makes sense, doesn't it? If you've got a lighter particle, it's going to move in a tighter circle. If it's moving faster, it's going to move in a wider circle. If it's moving slower, it moves in a tighter circle. This is the foundation, really, of a mass spectrometer. So if you've got a mass spectrometer and we've managed to get some particles which are all moving at the same velocity, so we can fix V, and I'll get onto how we do that in a minute. So let's fix V. Let's fix our magnetic field that these charged particles are moving in. So we've got control over these things, V and B. Then we're going to get circular paths which are going to depend upon the ratio of the mass to the charge. Mass of charge, ratio of mass to charge will determine where the particles will end up. So if we set up a detector along here, we can measure the radius of the path, the radius of the circular path, and that radius will tell us about the mass to charge ratio of that particular particle. So that is the foundation of a mass spectrometer. The only thing we need to work out how to do is, well, how do we get everything to have the same velocity in the first place? And this is where you use a thing called a velocity selector. So you've got a whole load of particles which are coming in through a narrow gap at a range of velocities. So they're all at loads of different velocities. You then set up, you'll have a couple of charge plates. So you'll have an electric field in here, and you'll also have a magnetic field. So you'll set up both an electric field and a magnetic field in this space. Now you calibrate the strength of those two fields for a particular velocity that you want. That if you get a particular value, a particular ratio of electric field strength to magnetic flux density, that will allow certain velocities of particle to go straight on. All other velocities will either go upwards or they go downwards, but they won't go straight on and through the gap on the other side. So you're selecting a particular velocity by changing the strengths of the electric and magnetic fields. So this is how we pin down a particular value of V to go into our mass spectrometer. We then, as I say, we got control over B anyway, because we decide what other magnetic field we want to put into the actual mass spectrometer bit where we're moving in circular paths. We can fix that B to whatever we want. We've chosen what V is, and now we're doing measurements of M divided by Q. So yeah, it's already pretty powerful just on this basic understanding of magnetic fields, and then how to construct a velocity selector with our knowledge of electric fields. And there we go, we've got a mass spec. And I mean, this is nice. They love it in exam questions because they're now linking two particular topics together. So this comes up loads because they're connecting together electromagnetism and classical mechanics in the same exam question. So expect to see quite a lot of this. Anyway, that's covered a lot of ground. I think the main things to remember from all of this is magnetic fields come from moving electric charge, or at least a changing electric field if we're thinking in terms of electromagnetic waves. But you need a changing electric field to get a magnetic field. We get this extra level of complexity around it, but really we're talking about magnetic flux density. This is really our magnetic field strength with a different name, measured in Tesla, as defined empirically when we're getting started by that formula. And we've got various riffs that we've just done on this. So we've got this F equals BIL sine theta, and then we've got this F equals BQV for an individual moving charge perpendicular to the magnetic field, and then moving into our circular motion off of the back of that. But remembering that that force, that resultant force, is perpendicular to both the current and the magnetic field, the external magnetic field. So yeah, there's quite a lot to take in there, but those three takeaways I think are the main things you want to have in mind, and then we can move all of this into the next video when we look at electromagnetic induction and transformers.